Hi there, and welcome back to Basic Math for Economics. Now we've finally done it. We've gotten through all of our matrix videos, and we are ready to finally discuss how to invert a matrix. So anyways, now we have our understanding of basic algebra and determinants with matrices, we're ready to just figure out how to do this inversion. And again, this is going to be a very useful technique that allows us to solve systems of equations directly. We can take an inverted matrix and immediately get our reduced row echelon form if we just pre-multiply. So it's a very neat technique. And again, this is commonly used when we calculate regressions in econometrics. So inverting a matrix requires 4 steps, and it's very useful to memorize these steps because you can call on them to just do them in order. First, we calculate the minors, then we reflect across the trace, we adjust signs, and then we divide by the determinant. Do them in that order, and you will get the correct inversion every single time. So let's walk through this. Let's start with a 2 by 2 matrix. So let's suppose we wanted to invert the following matrix. I just have A, B, C, and D as my 2 rows and my 2 columns. Well, let's calculate the inverse of this matrix. So first step, I need to calculate the minors. So in order to calculate the minor for a matrix, I need to get the determinant for the submatrix that encompasses all elements that are not in the same row or column as our current element. Now that's a really complicated definition, but it's actually really straightforward and easy. So especially for a 2 by 2 matrix, it's very easy. So let's work through it. So I want to calculate the minor for my first element of this inverted matrix, so where A was. Now, in order to figure out what that minor needs to be, I need to look at every element that is not in the first row or the first column. So I eliminate A and B because they're in the first row, and then A and C because they're in the first column. And I'm left over with just D. So I need to make a submatrix that contains just D. It's a single element matrix. And from there, I needed the determinant of that matrix. Well, the good news is that the determinant of a single element in a matrix is just that element. So the determinant of the matrix D is just D. So that means that the minor for my first row and my first column in my matrix is just going to be D. And that's it. That's all I need to do. Now I can follow that pattern, continue the process for each of my other elements, and I get all of my minors organized in the matrix as D, C, B, and A. And that's it right there. We are done with the first step. So, all right, let's move on to step 2. Next, we need to reflect across the trace. So the trace of the matrix is just the positive diagonal. So it's going to be whenever you have the same row and same column in the matrix. So D and A currently are my trace. So I'm going to take everything that's not on the trace and reflect it. So I'm going to swap the element in row 1 and column 2 with the element in row 2 and column 1. Now that's easy in a 2 by 2 matrix because you only have 2 things you need to swap. But in more complicated matrices, you just need to make sure you're reflecting it correctly. So that's going to update my matrix now to D, B, C, and A. All right, we're done moving units around. The third step is we need to adjust the signs. So this is a bit more complicated, but it's actually got a really nice pattern. So I'm going to multiply each term in the matrix by -1 to the r plus c power, where r is the row of that element and c is the column of that element. So the neat thing about this function is it can only take 2 values. It can be 1 or it can be -1, depending on whether r plus c is even or odd. If r plus c is even, it's going to be 1. If it's odd, it's going to be -1. So for example, the element in the first row and the first column on the matrix is multiplied to the -1 to the 1 plus 1 power, or -1 squared, which is just equal to 1, and so on. Just iterate your rows and columns. It creates what we would call a checkerboard pattern. We alternate between positives, pluses, and minuses, basically. So when I do that, I update my inverted matrix. So D gets multiplied by 1 because it's row 1, column 1. The B gets multiplied by -1, becomes -B because it's row 1, column 2, and that equals 3. The C gets multiplied by -1 because it's row 2, column 1, and again, so -1 to the third power. But the A gets multiplied by 1 because it's the second row, second column. So 2 plus 2 is the fourth power, -1 to the fourth power is just 1. All right, and that's it for that step. And lastly, we need to divide by the determinant. And again, I remember in previous videos I said that a determinant is very important for a matrix, or inverting a matrix, and this is why, because we have to divide by it. So it's going to be the determinant of the original matrix. So that's why it's usually useful to calculate the determinant first. In fact, if you wanted to calculate the determinant first, you're more than welcome to. But just recall that the determinant of a 2 by 2 matrix is just A times D minus B times C in this case. So it's a very straightforward one, and that number is a scalar. So I just divide each element of the matrix by that scalar, and that gives me my final inverted matrix of the first element is D over AD minus BC, then negative B over AD minus BC, negative C over AD minus BC, and then A over AD minus BC. And that is my inverted matrix right there. And that's all there is to it for calculating it. Now I say all there is to it, it's actually quite complicated, but it works. So let's actually do one a little more complicated. Let's do a 3 by 3 matrix. Now to save on notation for this one, I'm actually going to put numbers into this. So here's our matrix right here, 2, 6, 4, 1, 8, 3, 5, 7, 9 for my rows. Let's invert this thing. Well, all right. Again, we're just going to follow our 4 steps to calculate our inverse. And honestly, the only step that gets more challenging is this first one in calculating the minors. To show you why this gets a bit more challenging, let's calculate the minor for the element in our first row, second column, which is the 6. So first I need to calculate the determinant of a submatrix that contains every element neither in this row nor column. So I'm going to get rid of row 1, which contains 2, 6, and 4. I'm going to get rid of column 2, which contains 6, 8, and 7. So I'm left with this submatrix of 1, 3, 5, and 9. So it's a 2 by 2 matrix. And from there, I just calculate the determinant of that matrix. 1 times 9 minus 3 times 5, which is negative 6. So as you can see, even though those numbers when I'm building the submatrix are not next to each other, I just assemble it into that matrix, bring them all together, and then I get the determinant of that matrix, and that's going to be my minor for that element in my new inverted matrix that I'm working with. So when I put that in, we get the first row, second column of our inverted matrix, and I can calculate the rest of my minors to get similar values. And again, this is great practice for you to work through. Calculate all the minors of this matrix, and they're all posted right here. So from there, we are ready to move on to the next step. And that step is reflecting across the trace. And again, this is just moving things across to where they're going to be, reflecting them. The element in the first row, second column needs to be switched with the element in the second row, first column. So there's nothing really special to that, nothing's really changed. We're just going to mirror it. So now I get my new matrix right here, 51, 26, negative 14, negative 6, negative 2, and 2, negative 33, negative 16, and 10. So notice that everything along the trace, the main positive diagonal, has not changed, and everything else has been mirrored. Okay, next we need to adjust the signs. And again, we do the same thing. We do the negative 1 to the r plus c power, and we adjust our signs. We go through that, we get our new inverse matrix. So 51 gets multiplied by 1, doesn't change. 26 becomes negative 26 because it's multiplied by negative 1. Negative 14 doesn't change. 6 gets multiplied by negative 1. Oh, it was negative 6 and became 6 if we multiplied by negative 1. Negative 2 doesn't change, gets multiplied by 1. 2 gets multiplied by negative 1 and becomes negative 2. Negative 33 doesn't change, it's multiplied by 1. Negative 16 becomes 16 because it's multiplied by negative 1. And 10 doesn't change because it's multiplied by 1. And we're almost there. The last step we need is to divide by the determinant. And again, it's a 3 by 3 matrix. We can use the formula from last time to calculate the determinant, and we'll find that the determinant of this matrix is equal to 6. So all I need to do, because it's a scalar, is divide each term in my matrix by 6, and I'm going to have our inverted matrix. So taking these numbers, dividing it by 6, we are done. We get our inverted matrix right here of 8.5, negative 4.33, negative 2.33, 1, negative 0.33, negative 0.33, negative 5.5, 2.67, and 1.67. And that's actually it. And we can use this technique for a matrix of any size. Just remember that in order to invert a matrix beyond a 3x3, it gets much more complicated. In fact, I like to use computer assistance even for a 3x3 matrix for inverting it. I can do a 2x2 by hand pretty easily. But check out the walkthrough after this. I'm going to show you how to use Excel to quickly calculate the inverse of a matrix. It's quite large. Anyways, that's all for this video. Thanks for watching.